Yeah, hello guys. Good morning. Probably good afternoon by the time you're watching this video. But this is physics 322, and that's mechanics 2. Yeah, sorry we have missed a few classes, and I just want to post this recording to serve as guide for class today. Today we're gonna start talking about the rigid body dynamics. Rigid body dynamics. And our reference would be from Martin McCall textbook, chapter 8. Yeah. So we would discuss what rigid body is and how to calculate some aspect of motion of bodies that are considered rigid. So I'll give you a quick definition of rigid body. A rigid body, if I can spell, rigid body is a system in which forces act to maintain the distances between its constituent particles. And that is to say, i.e., their relative motion is constrained. Relative movement is constrained. All right. So earlier we've talked about motion of what we considered a particle and how it moves in one dimension and in 2 and 3 dimensions using vectors as our guide. And after that, the last topic we discussed is the two-body motion, and we used the example of the dumbbell, and then we talked about relative motion, and we talked about center of mass. So now we're going a step further. We're discussing systems. So a system is something made up of multiple parts, not just two parts like a two-body system. So a system will consider rigid body systems in this topic, in this chapter. And for a rigid body system, let's see, a very good example is a bicycle. So when you think about a bicycle has many different components. It's got a handle. What else does a bicycle have? It has, of course, it has a frame. But most notably, it has the wheels. And then there's a place for people to sit. So if you look at this bicycle would be considered a system. And within this bicycle, we can also take out separate systems. Let's take out this wheel. This wheel usually would have what we call the spokes. So the question is either taking out this wheel or taking out the whole bicycle as a system. How does this move? What are the dynamics of this? And we would notice for rigid body dynamics, there are two types of motion. So note two types of motion. The first one is the acceleration of the center of mass. So the center of mass moves, and that moves under the influence of the applied force. So the acceleration of the center of mass by applied force And 2 is the torque due to external forces acting through the other points of the system. So there's a torque. I believe everybody knows the meaning of torque. That's the force that is on rotating objects. So the second part is the torque due to external forces acting through other points of the system. All right. So we are going to write equations that describe the force and the torque. But before we do that, I want to reintroduce us to the kinds of variables that we would be using in writing our torque and rotational inertia and so on. So those variables are the variables that I call the rotational variables. So let's do a review of rotational variables. So what are rotational variables? When you think about the study of motion generally, we said that to be able to study and understand motion of objects, we're going to use some quantities, which are variables that we need to describe how the object moves. And we talked about position or location, distance or displacement, velocity or speed, acceleration, and how all of these are related with time. And if you guys remember, that's really the focus of Physics 213, Physics with Calculus 1. So this time around, we're going to write those variables again. The only difference here is that we're going to write these variables as the rotational ones. So in Physics 213, you learned about position. For the rotational variable, the first variable we'll talk about is the angular position. Angular position. And we're going to call that theta. So theta is simply given as S divided by R, where S is that part of the curve on a circle, and R is the radius of that circle. So if you look at this shape here, this is your theta, this is your S, the length of this arc, and then this is the radius, R. And note that this angular position is given in a radian measure. Radian measure. So we know how to relate angular position theta to degrees and revolution. And the relationship is that 360 degrees, which is a revolution. That's one revolution. That is equal to 2 pi radians. Okay. So our first rotational variable of interest is angular position, and it's measured as theta, which is the ratio of the arc subtended to the radius of the circle. So the second rotational variable that we'll look at is angular displacement. So angular displacement is just simply change of angular position, and that's final position minus initial position. The next rotational variable would be angular velocity. And what is that? Angular velocity, we're going to call it omega and omega average, so average angular velocity, is equal to the rate at which angular displacement changes. So rate of change of angular, that should be dt. Okay, good. And that's the average. We can write the instantaneous simply as omega equals delta theta, d theta dt. Okay, and that's instantaneous angular velocity. Okay, and next we can write our angular acceleration. Angular acceleration, alpha, the average angular acceleration will be change in angular velocity with respect to time, or the instantaneous alpha equals d omega dt. All right, so now that we've been able to write that, we can actually write equations to describe different things about rotation. For example, we can write the kinetic energy of rotation. So kinetic energy of rotation, just from, remember, kinetic energy is half mv squared. But for rotation, we would write kinetic energy of rotation, K equals 1/2 I omega squared, where I is the rotational inertia or moment of inertia. Of the body. So I is given as the summation of mi ri square, where mi is the mass of the particle or part of the system, and then ri is the distance from the particle to the reference point of measuring. So we'll spend some more time learning how to calculate the rotational inertia or the moment of inertia, and with this we would be introduced to parallel axis theorem. And then you guys will solve a bunch of problems. But we'll get to the parallel axis theorem later. But I want to talk a little more about torque. So let's talk about torque. So in describing rigid body dynamics, we know things will be moving, and we introduce torque as the force on an object that is undergoing rotation. So torque is actually defined as is the rate of change of angular momentum. And that's the same thing as the force multiplied by displacement. All right. So to write this, we need to be able to write an expression for the angular momentum. So let's attempt to write the expression for angular momentum. We're going to start. So by the way, angular momentum is L. L is used to represent angular momentum. So let's start from Newton's second law. Newton's second law says F equals ma, mass multiplied by acceleration, which is the same thing as mass multiplied by dv dt, right? Which, since mass is a constant, we can rewrite this as d dt mv. But you guys remember that mass multiplied by velocity gives us the quantity that we call momentum, right? So that this force can be rewritten as the rate of change of momentum. Okay? So now, let's now write this, an expression for force multiplied by displacement. We're going to take this as the force, and then we're going to multiply it by some displacement r, let's just call it ri. So now it happens that the force times displacement becomes force multiplied by displacement. We're going to write this as the r, that is the displacement, multiplied by external force, and that is given as, we can write r multiplied by the d dt of the momentum. And we can rewrite that as, so we can bring the r and momentum into the same time derivative. So d dt r1 cross p1. So, but note that r1 cross p1, which is really the reason we wrote this in this form, that is the angular momentum. So that total angular momentum would just be the sum of all these r cross p's. So that would be r1 cross p1 plus r2 cross p2 plus all the way to rn cross pn. N is the number of particles that make up our rigid body. So now we are going to write the total torque. And we represent that as G. G total will be equal to the time derivative of total angular momentum. All right. So this is our expression for the torque. Now, from this we can simply write torque G equals dL dt. Yeah. But we know that our L, angular momentum, is really mvr sine theta. And I want you guys to convince yourselves that this is actually a good expression for that. How would you do that? So mvr sine theta, that's really the product of the vector product of mv. Yeah. So again, convinced yourselves, i.e., prove this relationship. Now, if you're having challenging to prove it, mention this to me whenever we meet in class. We'll go through it together. But so we can rewrite our G as M dv dt r sine theta, since G is d of all of this dt. All right. So when you look at this, this is dv dt is a. So our G equals ma multiplied by r sine theta. Ma from Newton's second law is force. If you turn this into a cross product, that just simply gives you force multiplied by the r sine theta is the displacement over an angle theta. All right, so note that when theta equals 0, what is the torque? G will be equal to 0, i.e., if there is no rotation, there is no torque. All right. So to the last question I have for you to end this session right now is that I want you guys to tell me what is the difference between torque and work. And in asking this question, I want you to note that they both have same unit, Newton meter. All right, so I'm gonna end this session here, and the next session will talk about total torque and center of mass and how to calculate the moment of inertia. And by then I'll give you a bunch of problems to solve. So bye for now.